Welcome back, guys. So in today's question, we have two 10-pound blocks A and B that are connected by a slender rod AB that we know we can neglect the weight, and we know the coefficient of static friction is zero point 0.3 for all the surfaces that we have in this question, and we know the angle theta in here is 30 degrees. In the A part of the question, we need to show that the system is in equilibrium when P is equal to 0. And in the B part of the question, we need to determine the largest value of P. So looking at this, we'll see that what's happening in here is by applying force P, the block A is going to move down, and therefore the block B is going to move to the left. And we need to find the highest amount of P in order to keep our equilibrium condition. So let's start with the B part of the question first, and that way we can find a maximum of P for any amount less than that we will be in equilibrium condition. So well, obviously from the A part, we know that we need to show that if P is 0, the system will be in equilibrium, and we already know that P is 0 in equilibrium. We just need to show it, which means our P has to be more than 0. So let's start with the free body diagram. As always, we're going to start with the free body diagram of block B, and for that we have this block that has a weight of 10 pounds. We have the normal force NB, and we have the force FAB from the rod. This angle we know is 30 degrees. Since the block B is moving to the left, our friction would be to the right, and we call it FB. And that would be pretty much all the forces that we have, and we can move on to our equilibrium equations. You're going to start with our Fy. So what we have in Fy is Nb, which is positive minus 10 pounds, the weight of the block, and also we have the y component of FAB, which we know is negative, so we'll have FAB, and the cosine of 30 will be the y component. And from here we can find the normal force. It will be 10 plus cosine of 30, which we know is square root of 3 divided by 2 times FAB. That's pretty much what we have for our y equations. Let's move on to our x, see what we can get from some of forces in x direction. So for x, we have FB minus the x component of AB, which will be FAB this time, sine of 30 degrees, equals 0. So from here, we get FB equals to FAB times sine of 30, which we know also sine of 30 equals to 0.5 or 1 divided by 2. So from here we can get FAB equals to 2FB. So we can simply plug in our FAB from the second equation to the first one, and for that we have NB equals 10 plus square root of 3 divided by 2 times FAB, which we know is 2FB. And we also know that FB equals to static coefficient times NB. We know in the question that the static coefficient is 0.3. And if we plug that in previous equation that we have, we can find our NB, which will be 20.82. So now we have the normal force NB, and from here we can basically find all the forces that we have. We can find FAB from our second equation. So for FAB we have 2 times FB, which we know is 0.3 NB, and that's how we find the FAB. Now that we have this, we can move on to the free body diagram of A. And from that we can find the unknown that we are looking for, which is P. So for A, let's start with the free body diagram of block A, and let's see what we have for A. So we'll have the same weight again for A as well. We have the force P that is applying, and the block is moving downward, the friction is upward, and let's call this the normal force for A. And this would be our FAB. Again, this angle will be 30 degrees. So what we found from the previous part was the amount of FAB, which was 12.49. Now let's start our Fx and Fy equation. So for Fx, let's see what we have for Fx in this block. So looking at the fx, we will have fab sine of 30 degrees minus na equals 0. Since we have the fab, na will be simply fab times sine of 30, and we know fab is 12.49. Sine of 30 again is 0.5, and from here we can find Na, which will be 6.25 pounds. And there is one more equation left, and that would be our Fy, which we should be able to find the force P that we are looking for. So for here we have the Fa plus Fab, this time cosine of 30 degrees minus P and minus 10 pounds. That's pretty much all the forces that we have. And moving from here, let's see what we get for P. So if you want to have P alone, we'll have Fa plus Fab cosine of 30 degrees minus 10. The only unknown that we have in here is P, since we can find the Fa, and Fa would be simply 0.3, which is the static coefficient, times Na. And if we do that from the first part, since we already have Na from our fx, we'll have 1.87 pounds. And from here, the only unknown that left is P. So our Fa is 1.87 plus 12.49 times cosine of 30, which is square root of 3 divided by 2 minus 10. From here, what we get for P will be 2.69 pounds. And this would be the max of P that we are looking for. So as I was saying, if we look back in here, the maximum of the P would be at the time that block B and block A are about to move. And for breaking that movement threshold, we have to go over the static coefficient. That's why all the coefficient that we have in here are static, not the kinetic coefficient. And what we found at the end was that the P has to be 2.69. So that's the max of P for staying in an equilibrium condition. So let's get back to the A part of the question. When the P is whatever amount less than 2.69, we'll maintain the system in equilibrium.